In this video, we will be learning about light, the components of light, and how they interact with one another. There are three types of light: waves, which is what we see with our eyes, rays, which is the reflected waves, and photons, which is particles of light. So when we have a wave, we have crests, which are these tops, and we have troughs, which are the bottoms of the waves. To measure the wavelength, we go from crest to crest or from trough to trough. Okay, so these are our wavelengths. Doesn't matter if you do crest to crest or trough to trough, just stay consistent in your measuring. So wavelength is measured in nanometers and is denoted by the lambda symbol. Frequency is measured in hertz and is denoted by a lowercase f. Now, frequency is the rate at which the waves come in. So as you can see in the diagram right here, the top one has a high frequency because more waves are coming in, and the bottom one has a low frequency because the rate of waves is not as much. An important equation that combines these two and explains their relationship is that the velocity or the speed of waves is equal to the frequency times the wavelength. It's an important equation to understand when dealing with waves. So when light passes from one medium to another, meaning from air to water, water to another liquid, syrup, it is refracted, meaning it changes direction because the speed of light is different between the two mediums. The index of refraction, denoted by a lowercase m, of a medium can be defined as the speed of light in a vacuum, which as you see right here is a constant 3 times 10 to the 8th, over the speed of light in a medium. You usually have to solve for this bottom, the speed of light in a medium. A common index of refraction to know is that the index of refraction for air is equal to 1. Okay? So ratios between the wavelengths, the speed of the waves, and the index of refraction of the waves is up here. However, if we take these last two ratios and we cross multiply them, we would get that C over N1 times N1 is equal to C over N2 times N2. Obviously, the ends cancel out with each other. You're left with C equals C. So if we were to take this and simplify, we would get the wavelength in medium 1 over the wavelength in medium 2 is equal to the speed of the waves in medium 1 over the speed of the waves in medium 2, which is also equal to the index of refraction in medium 2 over the index of refraction in medium 1. Now pay close attention to this last fraction here because it is flipped with medium 2 being on the top. This is a very important ratio to understand when comparing different mediums and how light travels within those mediums. So let's apply these ideas to a problem. This says that a helium neon laser beam has a wavelength in the air of 633 nanometers. It takes 1.38 nanoseconds for the light to travel through 30 centimeters of an unknown liquid. What is the wavelength of the laser beam in the liquid? So first, let's write out our knowns. In this problem, we will call medium 1 the air and medium 2 the unknown liquid. So we have the wavelength of medium 1, 633 nanometers. We have the time in wavelength 2, or the time in medium 2, 1.38 nanoseconds. However, we want that in seconds, so we'll multiply times 10 to the negative 9. The distance traveled in medium 2 is 30 centimeters. We want that in meters, so 30 meters. We are solving for wavelength in the medium 2. And these are all of our variables. So when looking at our ratio right here, we need to solve for one of these variables. We have the distance traveled and the time that it took for that distance to be traveled in medium 2, so we can go ahead and solve for the velocity in medium 2. Velocity is equal to change in distance over change in time. So if we were to plug our variables in, we would get our final value to be 2.17 times 10 to the 8th. Velocity is measured in meters per second. So this would be our answer for the velocity in medium 2. So now for step 2, we will use that velocity to solve for one of the variables. So we can use velocity to solve for index of refraction. So remember, index of refraction is c, which is the constant, over the velocity. So if we were to plug our values in, we would get a value of 1.38. Index of refraction has no units. So let's write that this is into. Okay, so now for the last step, now that we have into and we have in 1, because in 1 it's going from air. Remember, the index of refraction for air is always 1. So let's write that over here for ourselves. In 1 is 1. And we have one of the wavelengths. We can use the first half of that ratio, where we say that the wavelength 1 over wavelength 2 is equal to N2 over N1. We cross multiply. Wavelength 1 times index of refraction in 1 equals wavelength 2 times the index of refraction in 2. Now we know that the index of refraction is 1 for medium 1, so we will just disregard that. And we have all these other values, so we will plug that in. And when we divide to solve for the wavelength 2, we get a value of 460 nanometers. And that is our final answer.